All right, so yesterday we finished up talking about hydroboration, oxidation of alkynes. And we said with alkenes, it's pretty simple. You treat it with BH3THF followed by peroxide and sodium hydroxide, and you always get anti-Markovnikov hydration, right? With alkynes, we said the same thing's true, but we have to use a new bulky reagent. Specifically, it's R2BH, which can either be this diisomylborane or 9-BBN, followed by the same oxidation steps. That gets you to your enol, where the alcohol is coming off that less substituted carbon, and then that will quickly rearrange into the aldehyde. So let's take a look at this enol to aldehyde transformation. This is referred to as a base-catalyzed enol tautomerization. So basically, we need to figure out how to get that enol to either a ketone or an aldehyde by using a base this time. So let's take a really simple example. And same thing, I'm going to draw all my carbons in just so we can keep track of them a little easier. And we're going to treat this with 9-BBN first, followed by sodium hydroxide and hydrogen peroxide. We know it's going to favor the less substituted carbon that I've underlined with blue. So we'll get an alcohol coming off there. And like we said, this is called an enol because it's half alkene, half alcohol. So merge those two together and you've got an enol. However, if you notice in this reaction, we've got hydroxide around. We don't have acid around. So this hydroxide is usually present in excess. And in fact, I'm going to show this full bond right here. And now what we need to do is figure out where the most acidic proton is on our enol. And I just gave you guys a big hint. Where do you think that is? It's on the oxygen, right? If we go through all of our acid-base rules from first term, right, we had those cardio rules. First one's charge. Doesn't matter here because they're all the same charge. Next one's atom. Oxygen's the most electronegative, so the proton coming off there is far and away the most acidic. So let's pluck off that proton with our base. And because this is acid-base chemistry, I'll show this with equilibrium arrows, because acid-base chemistry can be reversible. All right, now this oxygen has a negative charge. We've got our conjugate acid, which is water. All right, so we know that this is the most acidic proton because the negative charge ends up on the most electronegative atom. Is there anything else stabilizing this besides the negative charge being on the most electronegative atom? Resonance, right? So let's draw the resonance structure. We can kick that negative charge over to the neighboring carbon. Now we've got a double bond here, carbon here. And this carbon now has that negative charge that the oxygen used to have. All right, so in this next step, we still have water floating around. That was our conjugate acid. This carbon with the negative charge can just steal the proton back from water. And we end up with hydroxide coming out at the very end. Sorry, let me zoom out on this a bit so you guys can see it. So we've gone from our enol all the way to the aldehyde. And let me be consistent. I want to show equilibrium arrows here too. And just like before, we saw we regenerated the acid and the acid catalyzed transformation. In this one, we're regenerating hydroxide. So the base is being regenerated, therefore this entire mechanism is catalytic. Just like we saw in the acid-catalyzed transformation where we said the ketone is always favored, it's similar here. The aldehyde is almost always favored over the enol. So let's make a note of that. So the aldehyde form is almost always favored under equilibrium conditions. Does that make sense? So the number one thing you need to look at when you're doing these reactions is whether or not you have acid or base present. If you have acid present, you need to do the mechanism we saw yesterday. If you have base present, you need to follow this mechanism. And it is important to remember that this is equilibrium conditions, so you can go forwards or backwards through this. And so the pod that I gave you today is asking you to go both forward and backwards, and you have to pick which mechanism you want to follow. But really, it's just a lot of fancy acid-base chemistry. And if you want to hang out after class today, we can even go through some of it in the study session. Make sense? All right, let's do some practice. All right, I'll do some practice exam problems here. Yep. So I'll make them worth 4 points. So you've got 9 BBN, NaOH, and H2O2. Got this big old empty box worth 4 points. We need to determine what the product looks like and put that in the box. So I'll give you guys a minute to do that, and then while you guys are working on that, I'll get the second problem drawn. This time we'll do the reverse, where you have to determine the starting material. And we've got 9 BBN, followed by sodium hydroxide and hydrogen peroxide. This time we're going to be making Yeah, that's a good question. For the top reaction, do you think you're going to get one product, two products? Yeah, for the equilibrium conditions, always try to favor the ketone or aldehyde. I don't really care about the enol. That's a good question. Yeah, that's a good question. So I like to number carbons so I don't lose them. So I've got 1, 2, 3 carbons coming off that ring system, right? All right, where's the double bond going to be? Which carbon? So the double bond to oxygen, I should specify. Oh yeah, off carbon 3. So let's keep the whole framework the same. 1, 2, 3. I'll number this 1, 2, 3. We know we should have a double bond to oxygen coming off carbon 3. All right, and we know there's an assumed hydrogen there, which makes sense because we know with these reactions we often get aldehydes out of them, right? So pretty straightforward. All right, now let's do the bottom one where it's backwards. We have to figure out what starting material we need. If you think you got it, give me a thumbs up too. H2O, HO. Oh, sorry, that should be H2O2. Yep.
How would you abbreviate the other source of fluorine we would use for this reaction?
Sorry, the other
Source of fluorine we would use for this reaction? So
oh, the diacetyl I'd have to look that up. Yeah. Klein, in his textbook, almost exclusively uses 9 BBN, though. And I believe the ACS is pretty similar. Yeah. So show of thumbs, who thinks they got the starting material here? All right. So just like before, I like to number everything. It is super easy to omit carbons on accident with these problems. So I'll just say 1, 2, 3, 4, 5, 6. All right. So that carbon chain should still be intact in our starting material, right? So 1, 2, 3, 4, 5, 6. Draw that in. We know off carbon 2 there should be a methyl group. So we've got our carbon chain that we have before. Where should the triple bond be? Between 5 and 6. All right, so I'll change this into a triple bond, and that gets me to my next point about pet peeves. What looks funny about this? Yeah, it should be 180 degrees. So if you do draw this, try to focus on having the correct bond angles. So this be 4, 5, 6, and there we go. So that would be our starting material. Make sense? Okay, so let's take a look at the summary we've got here, because we did learn quite a bit. So we said if you've got some sort of alkyne that looks like this, you've got two different types of carbons. You've got this red carbon that's more substituted and this blue carbon that's less substituted. We said we can get two different products. One where we hydrate the blue carbon, in which case we end up with an aldehyde, right? And then another one where we hydrate the red carbon, where we end up with a ketone. We said in order to get the aldehyde, we'd use 9 BBN. Followed by an oxidative workup. For the bottom one, if we want the ketone, we need what? Yep, so we need mercury sulfate. Mercury 2 sulfate is our catalyst. And then what else? It's actually a pretty strong acid. So we need some sort of strong acid. What's a good strong acid that's available in most labs? Yeah, or even sulfuric acid. This is a more common one.
You said
It's
it's Hg2SO4?
HgSO4, but its charge is 2, so oftentimes people will call it mercury 2 sulfate. So we'll take sulfuric acid, water, and then that mercury 2 sulfate and mix it all together, and voila, you end up with a ketone coming out of it. Make sense? All right, let's do the same thing for a slightly different system. So now the question is, what happens if we have an unsymmetric alkyne? And we try to do each of these. Again, I want to be consistent, so I've got a red carbon right here, a blue carbon right here. We said for the top reaction we can do 9 BBN. All right, which position do you think is going to get hydrated? Or do you think it matters? Yeah, you get both, right? One's not more substituted than the other. So you'd end up with one where it would come off that red carbon. That would look like this. And then you would end up, so we've got this red carbon here, right? Blue carbon right here. And then another one where maybe it would come off that blue carbon. So this can be used to make ketones as well. However, if you do this, it's really, really hard to control which isomer you're going to get, right? All right, let's think about it this way. What about if we use the alternate conditions? So sulfuric acid and water and mercury 2 sulfate. What are we going to get? Or will it be the same? Yeah, it'd be the same, right? In this case, we don't have a clear distinction about which carbon's more substituted than the other. And so we lack all control in this situation. So one big takeaway I wanted to point out is if you have an unsymmetric system like this, you'll end up with a mixture of products, and you have to pay attention to both products that could come out. So in this case, we'd get two products which are constitutional isomers. What happens if I swap out this CH3 group for a phenyl group? So let's say it's now symmetric, where it has two benzene rings coming off each side. Will I still get a mixture of products? No, because both of them will be identical to one another, right? So this is really only a problem with unsymmetric alkynes. So I did want to leave that as a take-home message here. Does that make sense? All right, so let's jump into a new reaction, but luckily it's kind of review. This is halogenation of alkynes. And let's review what we learned last chapter. We said if you've got an alkene, in fact, I'm going to make it like this. You can add bromines across in an anti-orientation by treating it with Br2, right? In this case, do I have to worry about a mixture of enantiomers? Why not? There are stereocenters, right? I definitely see a stereocenter right here and right here. It's a meso compound, right? If I take this and I spin it around, it would look like this with two bromines as wedges. All of a sudden, we've got an internal plane of symmetry, so it's just a meso compound. We don't have to worry about enantiomers with meso compounds, so I'll just erase that. Say, all right, we get two bromines adding across the pi bond in an anti-orientation, and we can end up with a vicinal dihalide, right? All right, let's do the same thing with alkynes. All right, with an alkyne, we'll just take a simple example here. I'll show all of our carbons right now. You can treat this with Br2, and we're going to use a special solvent here, CCl4. This is carbon tetrachloride. It's almost completely phased out of organic chemistry because it causes a huge number of environmental and health problems. Mainly, it's been proven to cause cancer. So it's not commonly used, but it is used in reactions where you want to avoid unwanted radical chemistry, and we'll talk about radical chemistry next chapter. So you do see it in particular when you're trying to halogenate an alkyne. Okay, so when we do this, we're going to add a halogen across. So you can imagine you could have maybe one bromine here, and then the other bromine there, right? Would this be your E or your Z isomer? It'd be your E isomer, right? Be E or trans, right? Doesn't really matter which one you call it in this case, but that would be your major product for this reaction. So I'll just write major. The weird thing with this is we actually know you get a second product. Where both bromines are on the same side, so the cis isomer. And this will be your minor product. We're not going to get into the mechanism behind this, and to be honest, it's not well understood. Most chemists believe that it involves some radical chemistry, and so you don't always get anti-addition for this first step. All right, what do you think happens, though, if you treat either of these with a second equivalent of bromine? Same thing again, right? We've got an alkene. We can halogenate alkenes with bromine. So you get two bromines coming off this carbon, two bromines coming off the second carbon along with the hydrogen that was originally there. So you can over-halogenate it. Alternatively, you can just do this in one step by using Br2 in excess and carbon tetrachloride to purposely overshoot the halogenation and go completely to your final product shown there. Does that make sense? All right, you honestly don't see these reactions very often because they don't really have much of a practical utility. Does anybody remember from lab, I think I told one section, where do we see brominated products in our everyday life? Where? Brominated vegetable oil. So you can brominate alkenes, and I say, do you find that in things like Mountain Dew and Gatorade? And that's used as an emulsifying agent to help mix the food dye in, which is an oil, with water. What's another thing you see brominated compounds in? Not quite. Fire retardants. So quite often, fire retardant material is highly brominated or highly halogenated, and that prevents it from being as flammable. Specifically, they tend to tag a lot of bromines on there. So your couch, your baby crib, all of that stuff has a bunch of this material embedded in so it doesn't burst into flames if it catches a spark. All right, so let's move on to a new reaction. Again, this is kind of variations on a theme. We can do ozonolysis with alkenes or alkynes as well. So let's review from last chapter. Let's say I've got the alkene that's shown here, and I treat it with ozone followed by DMS. That's dimethyl sulfide, or you can use zinc and water. It doesn't matter. You just need some sort of reducing conditions. What will the product be, or products? Essentially, we can cut this in half, right? So we can say, hey, one half would look like this. The other half would look like that. What's the relationship between these? They're identical, right? So what we can do is we can make ketones or aldehydes. In this example, they're identical, right? So I'll just make a note there. That way we don't always think they're identical. All right, let's take a look at what happens when we do the same thing with alkynes. All right, so I'll take our simple alkyne that we've been using. Actually, I'm going to color code this. So I've got a blue carbon here, red carbon here, and this red carbon's got a proton coming off of it. What we're going to do, just like we did before, is we're going to cut this triple bond. When we do this, we're going to treat it with ozone, step one, and then in step two, we actually don't need strong reducing conditions. We can just treat this with water. Water is plenty good enough. When you do this, you're going to take this blue carbon, and you're actually going to oxidize it quite a bit into this new functional group. What is this? Carboxylic acid. All right, now we have to think about the red carbon. All right, the red carbon is going to get over-oxidized, so we're going to try to attach as many oxygens onto it as possible. What do you think this might look like? CO2. Oops, let me color code it correctly. So in this reaction, we're generating a carboxylic acid and CO2.
So the H that forms the alcohol on the blue C is from the red C.
Are you talking about this? That actually comes from the water workup. So step 2, it gets its proton from there. It's a little bit complicated, to be honest. I'm not going to get into the full mechanism behind this, but this is a new mechanism or a new way of making carboxylic acids. Currently, we don't have a good way of making carboxylic acids. So this is the first reaction we've seen where we can make that new functional group. All right, let's take a look at another example. And again, I'm going to make this a exam problem here. We got O3 followed by water. And in addition to doing this reaction, I want you to give me the name of our starting material and then our product or products.
Yep. What happens if you treat a benzene ring with ozone?
It's a good question. Somebody else asked me this today too. Do aromatic rings do these reactions? And the simple answer is no. And when you think about an aromatic ring, the reason it doesn't is it has resonance, right?
Yeah.
So the double bonds in an aromatic ring aren't really double bonds. In fact, they're more a bond and a half. So they don't do the same reactions that we see with alkenes and alkynes.
Okay.
However, we will learn those reactions later on this year.
I thought that's how we unzipped it. Or undid a ring. Was using ozone.
Not exactly. You can cut a true double bond, one with no resonance. But as soon as there's resonance and it's not a true double bond, it doesn't react the same way. Okay, show of thumbs. Who thinks they got the product here? Or products? All right. So let's start with the reaction and then we'll get to the naming. All right, I like to color code my carbon. So I've got a blue carbon here, a red carbon there, both sides of the double bond or triple bond, right? All right, so let's focus on the blue one. I know I've got this blue carbon here. We're going to oxidize it. So it's going to react and form a carboxylic acid. And in addition, what else should be attached to it? The methyl group. Okay, so I'll say CH3 is coming off that side. Now we'll focus on the red carbon. The red carbon, we know, also has this isopropyl group on it. And then what else do you think is going to be attached? Carboxylic acid. So if we go back up and we look at the previous example, we got CO2. Why aren't we getting CO2 with this bottom one? Yeah, we don't have a lone carbon with only a proton on it, right? So what we call these ones up top is this is a terminal alkyne. Terminal alkynes will give you CO2 because they've got that carbon on the end with the proton. This one is an internal alkyne. Internal alkynes mean that triple bond is between two carbon groups, and that means you'll get two carboxylic acids. And if that alkyne isn't symmetric, you'll get two different carboxylic acids. Does that make sense? All right, so now let's take a look at the name here. We've got to come up with a naming system. Should I number going left to right or right to left? Left to right? Okay, so I'd say, all right, I'm going to go 1, 2, 3, 4, 5. Why do I number it that way rather than going right to left?
Because you want the triple bond to be, or the alkyne to be closest.
Yeah, exactly. We want the alkyne number to be at the lowest possible position, right? So in this case, the alkyne starts at carbon 2. That's the best case situation. All right, we've got a methyl group coming off of 4. So immediately we'd say, all right, this is going to be a 4-methyl. And then what comes next? 2-pentyne. And there we go. We've got our full name as well as our products. Make sense? Yep.
So can you always conclude that the left side of the triple bond is always going to be a carboxylic acid?
Well, it depends how it's oriented, right? So anytime you've got a triple bond where one side of it is attached to a carbon, that side will turn into a carboxylic acid. And then if you have a side that's not attached to a carbon, that carbon will turn into CO2. Yeah. All right, so now I'll give you guys a challenge problem. starting from an alcohol, with 5 carbons or fewer, make this compound. And no cheating, you have to use the reactions we've learned.
What do you want us to do, Ben?
I'm guessing there's a different reaction that's much easier or
Yeah.
something.
You can get there in one step using a reaction we'll learn later, we just haven't learned it yet. I think chapter 13 will learn how to make this in one step from an alcohol, but for right now we got to do the long way.
So what, on a final, we can just do this one step?
Yep, we'll learn. I mean, there's oftentimes, it's like a highway system, right? We're learning all the different routes to get from point A to point B.
Well, that's organic chemistry, I guess.
All right, do you guys want to try doing this as a group now? All right, so let's work backwards and say, all right, how can we make a carboxylic acid? Well, we just learned one way, right? We can do ozonolysis, so we know in order to do that we need ozone followed by water. And when we do this, we can make a carboxylic acid, right? However, we always lose at least 1 carbon when we do the ozonolysis, right? Because we're cutting things in half. All right, so when we look at this, we've got 1, 2, 3, 4. So maybe we add a 5th carbon on there. So let's say, all right, maybe we started out with 1, 2, 3, 4, 5, right? And when we did this, we took this blue carbon right there. That's now the carbon that's in our carboxylic acid. What do you think happened to this red carbon right here? Yep. It turned into CO2 and probably just bubbled out of your solution. So we lost that 5th carbon as CO2. Okay, so now the next thing we've got to do is figure out how to make this alkyne. How did we do this previously on our pods and things like that? Yeah, sodium amide. So we could do that. So NaNH2 in excess, do a double elimination. Do we need the water step? Yes, because that carbon number 5 does have a proton on it, so we want to make sure that remains on there. So we'll reprotonate this with water. And just like we saw before, in order to do this, we need to have a dihalide, right? And I'll number this just so we're keeping track of everything. We still have the same number of carbons. Now the carbons 4 and 5 are going to turn into a triple bond by doing a double E2 elimination. All right, working backwards some more, we know we can make this from an alkene by doing halogenation. So we can say maybe this was just a normal double bond before. Yep, yes, Br2. All right, and now the question is, all right, how can we get here from an alcohol? Well, there's a couple different alcohols we can use. We could have an alcohol that looks like this, or we could have an alcohol that looks like this. Which one do you think might be a better route? Sure, maybe the bottom one. Honestly, you can do either one, but let's just, for the sake of argument, do this one. What could we do in order to turn that alcohol into an alkene?
Acid-catalyzed bitters.
So we're going this direction, right? So you could use strong acid and really, really high heat. That's one way. What was another way we could do? Yeah, so let's do both options. We could say catalytic acid and heat, or we could do tosyl chloride, convert that alcohol into a good leaving group, and then treat it with some sort of strong base, right? So I'll just use maybe sodium hydride. Either way, we can get that alcohol to pop off and result in an elimination product, right? So as you're seeing, a lot of these synthesis problems are kind of repetitive. They pull from the same stuff over and over again, and that SN1, SN2, E1, E2 chemistry is not going away. It is an essential tool that we use with synthesis. So if you are rusty on E2 chemistry in particular, make sure you go back and review that. All right, I think we'll stop right there. If you do want to stick around, I'll be here for about an hour to do review questions. If you do want to make one-on-one appointments, I'll be around tomorrow too.